Let's do a centripetal motion example problem, which I have helpfully written on the board already. So we have a rock swinging around in a circle on a 1 meter string at a constant speed. Our rock has a mass of 250 grams. It swings around 3 times a second. So, 1,000, something like that. So we want to know, what is the centripetal force and how big is it? Ignore gravity. So we're pretending there's no gravity in this problem. When I say what is the centripetal force, I mean like what flavor of force, what kind of force is it from our different forces that we've learned about. All right, so let's erase this. So we'll start by drawing a little picture. So we have a circular path the rock is following, and maybe we'll draw it over here. So here's the rock, there's a string in the center, and there's maybe some person there swinging it around or something like that. So maybe our rock has some speed over there. We don't know how big that is, but maybe we'll want to find that out. Okay, next thing we might do in a force problem is to draw a free body diagram. So let's see, forces we have on the rock. Well, the things touching the rock are the string. So we have the string, that's 1.0 meters long. So we have some tension that, if I'm copying how it is for this picture, the tension force is pulling it to the right. And what other forces? Well, I don't have anything else touching the rock, so there are no other contact forces. And it explicitly said to ignore gravity, so there are no other long-range forces. So our tension is the only force. This is the complete free body diagram. The direction of tension is changing as we go around the circle, right? Up here, the tension is down. Over here, the tension is to the left. But tension is the only force. So the answer to the first part of the question, what is the centripetal force, or which type of force is the centripetal force? The answer is just tension. So now we want to know how big that force is. Okay, so if we have this rock going around in a circle, we know the acceleration is towards the center at all points. That's just how circular motion works. So at each of these points, we have some centripetal acceleration. I don't have to draw that many of these. And this centripetal acceleration is happening because of this force, right? Newton's second law is that the net force is equal to ma. In this case, our only force is tension, and our acceleration is this centripetal acceleration. So for this problem, to find the force, we need to find out what this acceleration is. We happen to have an equation for centripetal acceleration. It is v squared over r. R we know, that was given, it's 1 meter. So we need to find our velocity. Now we know the rock is going around this circle with constant speed, which is, v squared, we can plug the speed in there too. That works equally well. So this is speed squared over r. So we want to find that out. How do we do that? To get this, we need to use a little bit of, I want to say, common sense math. We haven't explicitly done this in this class, but this is, hopefully the step that I'm about to do makes sense to you. This shouldn't be surprising. We know for this circle that one trip around this circle means the rock has traveled one circle circumference, or, yeah, that's the word I want, circumference. And the circumference of a circle is equal to 2 pi r. So that's equal to 2 times pi times 1. I didn't really need to write that, which is equal to 6.28 meters. So each lap around the circle takes, or it is a journey of 6.28 meters. All right, so it is doing this 3 times a second. So in 1 second, it is traveling 3 times 6.28, which equals 18.8 meters. So if something is going 18.8 meters in 1 second, we wait 1 second, 1,000, it goes 18.8 meters. That means its speed has to be 18.8 meters per second. Or, the v equals the distance over delta t. So 18.8 meters per second is pretty fast. That's like 40 miles an hour. And the rock weighs about half a pound, so I would not want to be standing too close to this. It would probably do some damage. All right. So we're ready to plug in for our acceleration now. Our centripetal acceleration is equal to 18.8 squared over r squared, that is 1 squared. So this is equal to 355 meters per second squared. That is a pretty high acceleration. That's significantly higher than the acceleration due to gravity, right? 9.8. And now we're almost done with the problem. We just need to plug in for the tension. So our tension force is, like we said, equal to the mass times this acceleration, which is going to be 0.25 kilograms. 250 grams was the mass, times the centripetal acceleration, 355 meters per second squared. And when I kept more sig figs and then rounded, I got a tension of 89 newtons. 88.8 newtons, 89 newtons, yeah. So I'm going to put an exclamation point next to that because this is a pretty big number, as it turns out. The weight of the rock, that is if you're holding the rock and feeling the force of gravity pulling on it, that is going to be 0.25 times 9.8, which is roughly 2.5 newtons. So the force that this is experiencing from the string is way, way higher than the force of gravity that would be pulling on the rock if there were gravity, but we ignored gravity in this problem. All right, so this is a good example of what a centripetal motion problem might look like. The sorts of variables we're dealing with here are pretty typical. We could complicate things by including other forces. The trick is that it's always the net force that's going to be in this centripetal direction. So there might be multiple forces canceling out and giving us a net force pointing towards the center. All right. Great. So yeah, hopefully this is helpful. We won't do more centripetal problems in the lecture videos, but we will see it again later in the course.